So I think it is then time for our next speaker, Professor Tony Jefferson from Cardiff University, who is the principal investigator of RM4L, a large-scale project which is running in the UK, and he will give us a few updates that are going on right now. So Tony, the floor is yours.
Or the screen even, yep. So, can you see a screen?
Yes, perfect.
Yeah. Okay, and it's not got any other extraneous things on it?
No, it's
no. Okay, so, right, RM4L, what's it about? Now, this, oh, my screen is not, oh, there we go. It is a study on the works of the Mozart. Just see who's listening. No, it isn't a study on the work of Mozart. It's a study on biomimetic materials, and it's funded by the UK Research Council, EPSRC. It started back in 2017, and we got about 16, 17 months to run, or 15, 16 months to run. And as Tim said, I've been asked to give you a bit of overview on the project. And so first of all, what was the provenance of it? Where did it come from? And it's worth knowing that just in order to see why we made some of the choices we did. Now, there was a preceding project called MM4L. So you can see how imaginative we are. We've gone from M4L to RM4L. But so that run sort of 2013 to 16 was led by my friend, now retired, Bob Lark. And that involved Cambridge, Bath and Cardiff universities. And what we did there was we concentrated on techniques to heal sort of different scales of damage, sort of the micro, meso, working up to macro. And then we looked at, in that project, the way we brought those things together was we tried to apply different technologies in some wall panels on site. The site was in South Wales next to quite a large road construction, highway construction project, which is just about finished now. And so these panels were not short of moisture at all. And but if you want to find out more about them, there's a couple of references there, and I believe that the slides are going to be shared. So I've given various references as we're going through, so you can look up more details. So that's what we did for that project, but not surprisingly, we haven't finished, and we haven't got lots and lots of commercial self-healing or biomimetic products. So we applied for more money, which is what researchers do, and so RM4L, then we wanted to, yes, create biomimetic materials that adapt to their environment, but we also wanted to look at immunity, a bit more about self-diagnosis rather than just concentrating on the self-healing aspects. So we took the analogy with the body a bit a bit further. So we think of cracked beans as wounds, and then our chemical, so infections we said were chemical, okay, and then aging, those of us who are, what shall I say, over 35, over 40, you start to feel the effects of it, senescence. So yeah, we wanted to explore that. And if you do too much running, you might get repetitive strain injuries, and that we sort of assigned to cyclic damage. So with that, we had to come up, the Research Council asked us to come up with a single slide to embody what we were doing. So this was it. So we created these various themes, and I'll talk about those a little bit more in a minute. And so then we have the basic technologies, we have scaling up, we have self-diagnosis, as I said, the self-healing ones, and the modeling and tailoring. And then we have the a bunch of applications that we wanted to look at. So that was the sort of framework that we set up. And largely, well, I say largely, we have been working with that, and that's served us reasonably well. So Who's involved in RM4L? Well, the research team is Cardiff, Bath, Cambridge and Bradford, a formal partner with us now. I've just put the emails of the lead investigators from each there, but all in all, there's 17 academics, 17 investigators as they're classed with EPSRC. There's, the numbers vary a bit, but it's about 15 postdoc researchers and 20 associated PhD students. But that does fluctuate as people come, people go. But that's probably pretty much the numbers at the moment. We have a number of partners, mostly industrial, but we have also other universities who are partners with us and research organizations. And then very importantly, we have an external scientific board, and if the slide isn't too small, you'll recognize a few names in there, and an industrial advisory board. They meet every 6 months and give us good steering advice that we take note of, and it helps us to shape the project. So I won't go through all these in detail, but these are what the research themes are. We have this one, which is really, they contain the RT1 has the basic technologies that we've tried to take forward from the previous research project, M4L. And but we've also got overarching ones like, you know, testing at larger scale, looking at applications. And you'll also, and design and modeling there, that's sort of close to my heart. And we added, after our midterm review, sustainability and life cycle assessment, and I'll say a bit more about that later on. And then we've got the sort of time dependent, transient loading, transient actions in general, cyclic actions causing cyclic damage. Then we've got the whole thing about trying to predict damage before it occurs and do something about it. Immunization is a word that's frequency of use has increased, I think, since this project started, for reasons we all know. And then not last of all, but the fourth is chemical damage, and we've heard quite a lot today already about the problems of corrosion. And if you can prevent, limit, reduce the amount of chemical damage, of which corrosion is the most common, we're well placed. Okay, so actually I'll get rid of that a sec. And so we've got a project, about 50 people involved. We're 4 years in, and I've got probably 10 to 15 minutes now to tell you what's being done. Now, I did look up our current publication list, which we have to keep up to date with the Research Council, and that is currently at 94. So what I decided to do was, we wrote a midterm review for the project, and that really gave some highlights. And I'm going to use those highlights, and most of those have now in the last few months, sort of, let's say over the last year, some in the last few months, appeared in print. So I'm going to use that to give you a flavour of the project, and then I'm going to tell you the way that we're steering it for the last part. Okay, so one of the things, so this work was done in Cambridge. So we had the first sort of UK commercial deployment of microcapsules. There was a lovely new building at Cambridge University for the engineering, and Abir, who leads this, leads the group at Cambridge, then secured access to some bits of the new building to put self-healing concrete in, and microcapsules with sodium silicate, but also did some tests alongside it. And if at the end, I'll show you all the references, but if you looked up reference 1, it describes these tests. And one of the things I did alongside was just to look at the effect of these microcapsules and their cargoes on improving freeze-thaw resistance. And the results for that, I mean, I've just taken one image from the publication, and this is the control without anything after 28 freeze-thaw cycles. This is with the microcapsules, and you can see it helps. That's what we all want to see. It helps. So that's the first thing I'm going to talk about. The second one are vascular networks. Now, we are doing some work on what I'd say standard vascular networks, but also we've gone in a different direction, and two groups. One, we've gone with mini vascular networks. That's something we're looking at in Cardiff. And they are like macrocapsules in the sense that they store reasonable volume. So if you looked at this thing, this tetrahedral, which with this tetrahedra thing that we've cut, that's about twice the size of the coarse aggregate particles. So it's about 45 mil. So that contains enough, if you distribute them throughout the concrete at a reasonable volumetric content, you have enough healing agent to heal macro cracks, sort of 0.2, 0.3, even 0.4 millimeter macro crack. Why do we call them sort of mini vascular networks and not capsules? We've certainly, with macro capsules, had problem getting the healing agent out. And the design of these ensures that a minimum of 2, generally 3 ligaments will always break when a crack crosses the unit. And if we've just got a little picture here from this paper by Christina, who works with us, and you can see the spread of healing agent here, and you never get an airlock because you always break more than 1 ligament and there's multiple paths. So we've found that very effective. The other work I've highlighted here is some work done probably in the first couple of years of the project, was looking at Murray's law. That was done in Cambridge, and using networks which you have parent and then child branches. And Murray's law is something that tries to minimize the resistance of the child branches. Those of us with children know that they're often resistant, so it's a good thing to minimize the resistance from them. So mathematically you can minimize the resistance of this system, and it gives you a mathematical way to optimize the network. And as you'll see, if you look up this and associated articles, you'd see it's quite an interesting way, an effective way. These were pressurized, certainly in some of the cases, to distribute healing agent and provide multiple paths which allow healing and rehealing to occur. So just making sure I can see the time. I know if Tim appears on my screen, it's like the chairman standing up in a conference, and you know it's time to wrap things up. Okay, what I'm going to talk about next is more work at Cambridge, and we've done a lot on microcapsules and put a large emphasis, certainly early on and continue to, on allowing them in the lab and also working with Micropore to be able to scale up their production and their ideas. They got some new facilities to do this, and the one I've sort of identified in the picture by Livia was this is a microfluidic setup, and you see here just a simple image of what happens in microfluidics with the capsules appearing here. And by having multiple branches, let's say, to create things, sort of scaled up greatly what can be done. And there was an interesting discussion on the way these are scaled up in this paper, reference 4. Our group at Bath, the approach at Bath's been quite interesting, because Kevin, who leads that, went off to talk to the microbiologists who knew, I won't say no, I'll say knew, past tense, knew nothing about concrete, but had worked with bacteria for years. And on that side of it, Suzanne Gebhardt works with us now and works with this. So her group really took a completely fresh look at bacteria and bacteria they were with, and they went around the world having another look at it from their microbiologist point of view. And they came up with some, they're not new in the fact they existed, but they're new to the self-healing word, the spore-forming bacteria that will produce calcite. And so, yeah, and they've had quite a lot of success with that. I'm going to highlight one of the findings from this paper here, that they found. They compared urolytic and non-urolytic bacteria, and found that the the irregular and perhaps the larger amount of deposit volumetric content of the non-urolithic, I've said it right twice, the you know, was beneficial for self-healing. So again, there's something to follow through there. I breathe a sigh of relief when I get to slides like this, because I know what's going on here. So this is a combined numerical experimental study. We've really tried to integrate the numerical and experimental side of what's going on in RM4L. Done a lot of work on this with Vascular Networks, trying to characterize systems, or that sort of, yeah, characterize an autonomic system, and we chose a particular system, and then study the various parameters and then build up models from it. And we've got a pretty comprehensive now new coupled transport mechanical finite element code. I missed element from here. Code that does this. We've focused a lot on varying transport in different cases, cracking in microcrack, continua, discrete cracks, what have you, reactive chemical transport also. And one of the things we have done is developed a new model that enables the effect of cracks moving as healing takes place to naturally be accounted for. And this is just a test, the green one's the model of 2 tests done, notched beams, vascular network, different CMOD opening rates, and look at the contrasting response of those. The measurement, being able to predict damage, is very important. This is there's a grouping bath that does this, concentrates on this, and it's quite difficult because the heterogeneous material that is concrete to get really good signals. But they've developed some new PZT devices and are now really with some certainty and accuracy starting to be able to predict damage and then repair afterwards. And you'll see this sort of the admittance signal there. The damage is very different from the repaired. Okay, when we were in RM4L, we looked at SMP tendons and saw what shape memory polymer tendons themselves could do at closing cracks. And but that was limited in terms of the amount of stress potential, shrinkage potential stress they had. So we took a different approach when we started RM4L, and this tendon here is formed by having a sleeve which is pre-compressed, and this one's with Kevlar, a Kevlar tendon, which acts as both reinforcement, but also the combined tension has some sort of pre-tensioning in it. And this is both very effective at providing reinforcement and very effective at closing cracks. And once cracks have occurred, these are activated sort of using heat, but electricity there. And there's a reference that provides some details of that. And now we've not just concentrated on sort of, how should we say, main concrete or whatever. Abia particularly has an interest in soil systems and has done this interesting work with SAPS on soil cement systems, focusing on cement bentonite cutoff walls for things like landfill or nuclear waste containment, and has shown that they're very effective at improving sort of wetting, drying resistance using SAPs. And I think the last one on this group, there's been a focus to try and find, try and just build in sensing into the cementitious material itself using graphene and natural graphite as well. And I've highlighted this work on looking at different scales of graphite inclusions, different finenesses of graphite inclusions. And this was very effective, provided you've got sufficient quantity, and there's some, you can look up the conclusions from this paper here, at actually making a member itself conductive. So there's much other work. I've highlighted some work on corrosion prevention, some sort of knotted SMP fiber reinforcement, some interesting stuff on carbonation with bacteria, and yeah, some looking at trying to make the structures subject to cyclic loading self-heal more effectively. So that was just one or two other things I mentioned, and I said that earlier, that there's 94 project papers currently linked to the project. So in the first half of this project, we very much weighted the work really towards trying to improve our basic self-healing technology, not solely, but certainly probably 60–70%. And in the second half, what we're doing now, we really are making big efforts on to do more work on transient, mechanical, environmental, detecting and immunizing and scaling up. And that's, yeah, it's keeping our attention and keeping us busy at the moment. And as I mentioned before, after the midterm review and some feedback, we had been specifically some work on sustainability and LCA, but we wanted to tie it together and make sure we were using more waste materials, low energy materials, properly conducting on LCAs on all our systems. Okay, so these are the references. I'll put them in there. If you have any problem getting hold of them, let me know, and that's fine. And yeah, I'm in time, and that's the end of the presentation on Mozart. Thank you very much.
Thank you very much, Tony. I was at first I was expecting a nice musical composition, but it turned into a very nice technical presentation. So thank you for that. I don't think we have received any questions in the chat, but I was actually wondering, you showed a comparison between, I think, experiments and modeling, specifically then where you looked, yeah, that one, where you looked at how a vascular network is behaving. But what are you then considering as a healing agent in this study? Because I guess it's something that needs to be able to react very, very fast.
Yeah, we deliberately chose a cyanoacrylate PC20 so that we could conduct these experiments quickly. Now, one of my, I suppose, contentions is that in nearly all cases, the cracks will move during the period that healing takes place. Not often in practice will loading and environmental conditions and temperature be completely static. So we wanted to study that, but we wanted to study it and do lots and lots of sort of cases. So we chose a fast-acting agent, which is the cyanoacrylate, and then we made sure that we could test quickly enough to effectively get the response of a control, and slowly enough, and I haven't shown the two extremes here, that you have the you know, a complete healing and then the classic re-cracking side. And then we looked at all these rates in between and then tried to build a model that would just naturally represent that with different crack widths. So you're right to point out that to do this, you need a fast-acting agent or a lot of time. So we chose the fast-acting agent and making the tests. Not many of our tests had durations of more than 30 minutes, many considerably less. But it did mean we could do literally hundreds of them to look at this range of parameters.
Okay, yeah, thank you for your clarification. That was very nice. So I think if any more questions will come in, they will come in via the chat. So then I would like to thank you, Tony.